Science time. Magnets. Let's write down magnets, please. So I already have some things on the board about magnets. And we talked about this a little bit before I started the video, but we're talking about magnets. And what do we call the force that powers magnets? Do you remember? We didn't really say it yet.
The North and the South Pole?
No, but what's this whole idea of this whole force is called?
Oh, the magnetic.
Yeah, the magnetic force, but it's coupled with another force that we talked about. Electric. And together they form the electromagnetic force. So this same force governs, and we'll talk about why they're related, but this same force governs both electricity and magnetism. So here we're talking about magnets, and I have some things drawn on the board already, but we said one of the things that's very important we understand about magnets that makes them so special and unique among forces is that they are what kind of force? What makes them so special? What makes them seem like magic? Yeah, they're a non-contact force. They're a non-contact force. What other forces have we talked about that are non-contact? I can really only think of one major one. Gravitational force. The gravitational force is also non-contact. So why does gravity not really seem like magic to us? And magnets kind of do.
Because gravity pulls.
Yeah, because we interact with it all the dang time, and for another thing, as Rhett says, it only pulls. So where gravity, I'm going to write this in a different color, gravity only attracts. Whereas, what? Magnetism, magnets can do what?
Attract and repel.
Attract or repel, depending on what?
What way they're facing.
Yeah, depending on let's think of a fancier word for what way they're facing. Depending on their
Poles.
Depending on the what of their poles.
Position.
Sure. Magnets attract or repel depending on the position of their poles. And so I have written up here, I think you can see this on the video. Yeah, you can. Here I've drawn this magnet. We generally indicate the south pole of a magnet with red. That's just kind of customary. There's nothing, that's not a physical property of the universe. There's nothing that says the magnet's got to be red on the south end. That's just kind of how we show it. So the magnet has a north and south pole. The north pole of one magnet will do what with the north pole of another magnet? What do we call it? North pole and north pole repel. The same poles repel. God bless you. The same poles repel. The north pole will do what with the south pole of another magnet? Attract. Opposite poles attract. Remember that. Write that down. Opposite poles attract. That's going to become very important, not just for this, what we call macro scale or large scale magnetism, but when we get down to talking about the parts of an atom, that little thing you're just writing down now is very important. Opposites attract. There's even, I'm sure, a song for old people about it. So, we also talked about how this magnet is made up of usually iron. We're going to put iron here. Cheap magnets are generally made of iron. The magnets you'll be using are made out of iron. There are such things, I was telling you earlier, there's nickel and cobalt can also be magnetic. Iron, nickel, and cobalt are kind of the common metals that we encounter as being magnetic. But there's also such thing as rare earth magnets like praseodymium and neodymium, which are down here. And they have long names, but these kind of make pretty good magnets. The best magnets that we are aware of are rare earth magnets. Anyway, some kind of metal, they're always metals, some kind of metal, in this case I've drawn iron, is making up this magnet. And basically what happens is the atoms all get lined up so that their electrons have a charge facing the same direction. So every single atom, I put one, every single one lines up their electrons, making a magnetic field. And we'll talk more about this idea about a magnetic field, but basically there's an area around a magnet that you can't see that exerts a force on other magnets. These things are magnetic, and so when they attract, or they should repel, they're just very weak magnets, but look how weak the stupid magnets are. And here, oh, there we go. I have them. Come on, attract. They kind of do. There. In this way that, oh, for crying out loud. Attract. Gosh dang it. Well, you can see, there. I don't know if you can tell that on video even. It looks like I'm just holding up two little blue squares, but they're repelling. You've seen magnets before, right?
Yeah.
Yeah, these are repelling right now. the way I have them oriented. And when they repel, they try to shift themselves so that they do what? They try to move themselves so that they are instead...
Can get magnet.
Yeah, so that they're instead attracting, right? So that they're instead attracting. And there's this three-dimensional field around the magnet that is exerting a force on all, not only the magnetic objects around it, but pretty much all the metallic, and there's exceptions to that, but pretty much all the metallic elements around it as well. That's why these stick to my whiteboard, because there's a metal backing to the whiteboard. And even though the metal backing of the whiteboard isn't magnetic, these magnets are attracted to it. So, what all this is getting at is if I take my angle grinder here, my beautiful, I'm going to write it in cursive because of how beautiful it is, angle grinder, and saw this magnet in half, while it's still going to have written on it north and south, this magnet is not going to have only a north pole, and this one is not going to have only a south pole.
It's going to change.
It's going to change. It's going to change so it has both, right? So this magnet, when I break it, will become these two separate magnets, each of which has both a north and a south pole, because the very atoms that are making it up have a north and a south pole. Is that clear?
Yes.
Yeah. Let's talk real quick about some different types of magnets, or some different types of magnetism. First of all, we have this idea of ferromagnetism. You understand, so these are iron atoms, but you're aware that not every piece of iron is magnetic, right? Like you can have like a steel nail, and you can't like, hang it onto your fridge by itself. Only when these atoms get arranged in this way is it considered magnetic? Can the thing itself be magnetic? And that's this ferromagnetism, is when the atoms line up so the magnet, well let's say so the object generates, what's that word mean? Creates its own magnetic field. Atoms line up so the object generates its own magnetic field. There's another idea of electromagnet. And even though we use the word electromagnetism up here to call it the force that covers all, if we're talking specifically about an electromagnet, it's when it only has it's a thing that only has an electrical field when electricity is powering it. Only has a magnetic, I'm going to abbreviate it, field when an electric current runs through it. Why might this be useful? When would we want it to have a magnetic field when we turn it on and no magnetic field when we turn it off? When would that be useful?
Maybe so you can turn it on and off.
Well, yeah, like I just said, you can turn it on and off. When would that be useful?
Maybe for like magnetic trains or whatever, or electric magnet.
Dump yard. Pick up the cards.
Yes, Leo. Yes. So you don't want that car to be stuck to the junkyard magnet forever, right? You want to be able to drop it eventually. What were you trying to say, Justice?
Electromagnetic trains.
Trains, yeah. We don't want the train to always scooch along at 1,000 miles an hour, right? We want to be able to stop and slow down and stuff. I was also thinking of, if you've ever had someone roof your house, which just recently happened to me, they go around they push around a magnet to pick up all the nails. But they don't want the nails to be forever stuck with it. They certainly don't want to go through and pick off the nails hand by hand. And so they want to be able to turn it on, run over all the nails, pick them up, and then turn it off when they're over the dumpster, right? Another thing that this happens is your speakers are electromagnets. When a current's going through them, it generates a magnetic field which makes them go up, and that generates a sound. But even the tiny little speakers in your headphones are doing this all the time. They're electromagnets. And then the other type of magnetism we're going to talk about, and I'm not really having enough room, but paramagnetism is when an object is affected by magnetic fields but doesn't have its own. Ignore that. Like what? What would be a paramagnet? So we talked about how these objects, I guess I'll use my little avocado. This is also a magnet. Oh man, these blue magnets really suck. Here, camera. Oh, avocado! Here's my avocado magnet. Here's my blue magnet, and they should. Yeah, nice. Oop. Perfect, yeah. This, I should have picked better magnets to do these demonstrations with. Well, pretend that it did it right. There we go. Is the whiteboard magnetic?
No.
It's not ferromagnetic. It doesn't exhibit ferromagnetism, right? It doesn't have its own magnetic field. This little avocado does, though. But the whiteboard is paramagnetic. It's affected. Can you think of something that isn't any of these? Basically, if we think just in terms of the little avocado, the avocado is a ferromagnet, right? It has its own magnetic field. So it's going to be attracted to two different kinds of things from here. Well, really all three of these. It's going to be attracted to other ferromagnets, like my blue eraser. It's going to be attracted to things that are paramagnetic, like the whiteboard. And it's going to be attracted to electromagnets. What is it not attracted to? Can you think of anything I could try to hook this to that it wouldn't hook to?
Gold.
No, gold is paramagnetic. This is a really easy question, or it should be.
Money.
Money, wood, yeah, me.
Anything that doesn't have
It looked like it stuck, but it didn't. That one stick because it's friction. That was not a very good example. But yeah, things that are not any of these will not interact with the magnetic field at all. Right? That's why I can only stick my avocado to the whiteboard and not to this plastic whatever. You see what I mean? So the whiteboard is paramagnetic. It interacts with magnetic field, but it doesn't have its own magnetic field. The avocado is which of these? Which of these is the avocado? Ferromagnetic. Ferromagnet. And your speakers are an example of an electromagnet. Do you have questions about any of this, Leo?
Yeah, is it bad when you put by your heart?
By a heart?
By your heart?
No, not generally. So there's only a little bit of research into this, but yeah, when people are exposed to very, very, very heavy magnetic fields, for just a little bit of time, it doesn't really normally hurt them. Like, if you're in an MRI, that's an extremely high magnetic field. But it doesn't hurt you if you're just in it for a little while. Eventually, there start to be some complications. Like people, like you said, your blood has iron, and so it kind of messes with your blood flow. Usually not very much, because hemoglobin itself is only very, very faintly paramagnetic. So no, there's no magnet that I can think of strong enough that you could like hold in your hand and hurt your heart or anything else about you. Magnetic fields are really safe for people, because we're not any of these, right? We don't really interact with magnetic fields. There are some people, I mean, I'd hesitate to say weirdos, it's kind of cool, but there are some people that have really strong magnets implanted in one of their fingers so they can detect magnetic field, and it becomes kind of like a sixth sense for the people. Like they can tell if there's a phone in the room because it will interact with the magnet. They get so good at detecting magnetic fields that they can, anything that has a magnetic field they can detect with their little finger magnet.
That is creepy.
That's not the point of why I'm talking about this, but magnets are non-contact forces, and so they seem like magnets. Right? They interact with things in a way that is sometimes unexpected because we don't very often have very much familiarity with them. Do you have other questions about magnets? So why do things have a magnetic field? Usually because of the way their atoms are lined up. Sometimes, as with Earth, it's because of the way it spins. Earth generates its own magnetic field, which is why compasses work. But in general, for the small scale things that we'll be doing in here, it's because of the way their atoms are aligned. Other questions?
No.
Okay, bye.